Let's start. Now, we start with last week, we talked a little bit about the photoelectric effect. Okay, so let's recap a little bit before we move on. So for the photoelectric effect, basically, it is an experiment that proves that light is a particle rather than a wave. Okay, so based on the wave theory, it says that the energy is from the amplitude, is proportional to amplitude. This is based on the wave theory of light. So the higher the amplitude, then the higher is the energy of the wave. And you can think of amplitude as the brightness. The brightness, if it's high, or the intensity, if it's high, then the light it has very high energy. Okay, so but then they found out when you shine the light on the metal, by right, if I keep on increasing the brightness, at some point the electron will be it will pop out. Okay, it will pop out because you have enough energy given to the electron, then it can escape from the metal. Okay, so according to the wave theory, if I just keep on increasing the brightness, then at some point I will be able to emit the electron, right? But it turned out that this is not the case. It turned out that no matter how you increase the brightness, if you're using a low frequency light, for example, like visible light, okay, or infrared, no matter how you increase the brightness, still the electron cannot come out, right? But if you change the frequency, you increase the frequency, then you start to see the electron jump out of the metal. So they concluded that there is a minimum frequency that you need to achieve to emit the electrons, and that they form another theory that is, they say, the particle theory. Okay, the particle theory, or you say the quantum theory of light. It says that the energy is not depend on amplitude. Energy depends on the frequency, E equals to hf. Okay, the Planck and the frequency of the wave. And the particle theory also says that it is not a wave, it is like a lump of energy, right? This ball of energy, it doesn't have mass, it doesn't have charge. It's just a energy packets moving, traveling. Okay, and one photon, this is one photon, can only be absorbed by one electron. Okay, it can only be absorbed by one electron. And also, it has to be very specific energy. Very specific energy level that the electron can absorb. Not all types of proton it can absorb. Only specific energy that it will absorb the photon. Okay, so that is the overview, okay, from the last lesson, a recap from the last lesson. Now we move on, and this is the extended part from the photoelectric effect. We will look at what is work function and what is threshold frequency. Right, let me position this a bit. Okay. Let's say we got two metal A and metal B. Now, metal has got many free electrons, so it's a very good conductor of electricity, right? Now, when you shine the light, now when I say light, it could be any light, ultraviolet light, infrared, okay, even X-ray also, they are, I'll just call them light, okay? So I shine the light here, and then the energy needed to emit the electron from each metal is different. Okay, metal A might need more energy than metal B. So it's different, the minimum amount of energy to get the electron out of the metal is because of the binding energy. Okay, binding energy is different from each metal. Some metal, they have higher binding energy, they hold the electron stronger, and some they have weaker. So that means the energy that you need to emit the electron is different. Okay, now this energy, right, the minimum energy needed to emit the electron is known as the work function. Okay, work function. Now, to emit energy, this wave, right? This wave, they must have energy equal to the work function at the minimum. If the energy of the wave is smaller than the work function of the metal, then there will be no photo emission. Okay, at least it must be equal to the work function. So again, what is work function? Work function is the minimum energy required for the electron to go out. Okay, to go out. All right. So we say that here, energy of the wave must be equal to at least the work function, right? Or it can be greater. Greater also it will emit. But if you less than, then there will be no electron coming up. So here I can write W equals to E, and we know that E is equals to Planck constant times into the frequency here, right? So if work function is the minimum energy required, then that means there is also a minimum frequency required of light, because the energy of the wave is you get it from the frequency, right? The higher the frequency, the higher the energy. So if there is a minimum energy required, then there's a minimum frequency required as well. Okay, so this minimum frequency, we call it as the threshold frequency. The threshold frequency. So what is threshold frequency again? It is the minimum frequency of light that you need to achieve to emit the electron from the metal, okay, to achieve this photoelectric photo emission. So we give it a notation. We will write the work function equals to h times into this threshold frequency. We put f naught. Okay, so this is your first formula, right? So the threshold frequency, and then you can calculate what is the work function of the metal. Every metal has a certain work function. So work function is like a characteristics of the metal. Okay, depends, it varies, depends on the type of metal. Okay, look at this bullet point down there. When a photon energy is absorbed by an electron, the energy is used to release the electron, and the extra energy will become the kinetic energy of the photoelectrons. Okay, you see here, let's say I have metal, the same metal, metal A. Metal A having a work function of W1. Now I have a light coming, having energy E, and you can calculate this using HF. So whether electron will be emitted depending on the E, right? So if E is equals to W, then there will be emission. Yes, emission occur. But because this work function is the energy used to just to release the electron, just to pop it out from the metal. Okay, so if you give it just right, the energy exactly equals to the work function, then you're only able to pop the electron out, but then there is no remaining energy. Okay, this is just enough to release the electron, but the electron doesn't have any extra energy to use because you just give all the energy just to release it. Okay, so if the energy is equal to work function, so emission will occur, but no extra kinetic energy. Yeah? No extra kinetic energy. Okay, now a different case would be like this. Same metal, same work function. Here, this one, I increase the energy of the light. Okay, I increase it. Okay, let's say energy is less than the work function first. Okay, so let's say this energy is less than my work function. Then what happened? If it's less than the work function, will there be emission? No, right? Because this is work function is the minimum energy. If you're giving less than it, then you cannot emit any electron. So here is no emission. No emission of electrons. So nothing happened. Nothing happened. Now, the third situation is when I supply energy that is larger than the work function. Okay, if energy is larger than the work function, then what happened? So say that work function is like, okay, 3 electron volt. You need 3 electron volt to emit the electron, but you're supplying it with 5 electron volt. So 5 minus 3, you got 2 electron volt extra, right? Extra. So where does this extra go? The 3 is already used to release the electron, and then the 2 electron volt extra, it will be the kinetic energy of the electron once it is emitted. So that means the electron that is released, they have kinetic energy of 2 electron volt. Okay, so electron volt is like the energy of an electron. So usually they use electron volt instead of joule. So that means if the energy is more than the work function, then you can calculate the extra. What is the extra? Extra, we can say that whatever the energy, you minus the work function, get the extra energy, correct? Okay, and this extra energy, it is represented, okay, it is absorbed as the kinetic energy by the photoelectrons. This is the kinetic energy of the emitted electron, the photoelectrons. Okay, so kinetic energy of photoelectron is equals to the energy that you supply minus the work function. Please remember these equations. In this chapter, this is our main equations here. KE equals to E minus work function. Again, KE is the kinetic energy of electron, and this one is the energy of the light shining in, and this is the work function of the metal. Okay. So if E equals to W, then KE equals to W minus W. KE is 0. That is the first case. If the energy is equal to the work function, then the electron will not have kinetic energy, but it will be released, but no extra kinetic energy. Okay, so this is the 3 different cases. The energy supply equal, less than, or more than the work function. Okay, so back to this point number 1. When a photon energy is absorbed by an electron, okay, the energy is used to release the electron. So it's like 5 electron volt, 3 electron volt is used to release, and the extra 2 electron volt will become the kinetic energy of the photoelectrons. Okay. Second one, electrons on metal surface will acquire maximum kinetic energy compared to the electron inside. Okay. Electron on metal surface. Let me erase this first. If you want to take a screenshot, you can screenshot it. I want to clear this, get more space. Okay. Just a second. Oops. Okay. Now, think of it like this. Let's say we use the same metal, our metal A. Now, just to simplify, I'm going to draw a few atoms. This made of 3 layers, okay? 3 layers of atoms. Now, here is our metal. We know that certain metal has certain work function. Okay, so let's just say that this the work function of this metal is W. Now the first layer, the layer closest to the surface, the outermost, okay, the uppermost surface, always have the minimum work function. And this work function will increase as you go deeper and deeper down. Okay, now let me make it clear again. Different metal, we are talking about a type. Different type of metal has different work function, correct? And for the same type of metal, for one specific type, if you go down the layer, the work function also will change. Okay, it also will change. It's never the same for each layer. Why? Because the layer closest to the surface is the easiest to emit the electrons. Okay, it's the easiest, just like evaporation is easiest for the molecules at the surface of the water to escape compared to the one at the bottom, at the deeper layers. Okay, same concept here. So the work function at the surface is the minimum. That means you need the least energy to pop this electron out. You need more energy to pop the electron at the bottom out from the metal. Okay, so each layer, the work function increases. Now back to our formula. What is our formula again? Ke equals to E minus W, like this, right? So if this W is minimum, this is same, right? Because we are using the same light. Okay, let's say we use the same light. So this energy is the same frequency, HF. If my work function is minimum, that means my kinetic energy is a maximum. Think about this. If this value is large, then I use this one minus this one. The value here is small. If this value, the W, small, okay, it is small, then when I minus it, I get more energy, right? So my kinetic energy is maximum. So the smaller the value is the work function, the higher will be the kinetic energy. So we write here minimum work function, you'll get a maximum kinetic energy. Where do you get minimum work function? At the surface, at surface of the metal, correct? Okay, at surface of metal. So that means the electrons at the surface of the metal, they gain the maximum kinetic energy. I repeat, electron at the first layer, the outermost surface, they get the maximum kinetic energy. Electrons at one layer deeper, they get slightly lesser, okay, from compared to the first layer. Electron in the third layer, less and less and less and less and less. Okay, because of the work function. Right. So whenever you see this Ke max, then you know we are assuming the photon emission happening at the surface of the metal. And for most of the example given in the question, they give you the work function. Okay, work function of a metal is 2.5 electron volt. This is referring to the surface. Normally they give you in surface, the work function at the surface of the metal. Okay, now if you are experiencing lagging, if it's very laggy, please let me know, because I'm not sure on your side is the internet okay or not. Okay, let me check real quick. Give me a second. Give me 1 second, guys. Because I feel like not very smooth. Okay, looks okay. Okay, we'll continue. Okay, do let me know if it's really laggy and you cannot hear anything. Okay, we'll restart and relog in. Okay, where were we just now? We were talking about the work function, right? Okay, so minimum and maximum work function. To get the maximum kinetic energy, it is at the surface of the metal where work function is minimum. Okay, so point number 2 here, electrons on metal surface, okay, will acquire maximum kinetic energy compared to electrons inside. Okay, now you know why. Why? Because of the work function is different for each layer. For the work function and threshold frequency, here, the first slide. How do you define work function? The first point here, the minimum energy required for a photoelectron to be emitted, okay, from a metal surface is known as work function. To be emitted into the atmosphere, okay, minimum is known as work function. And the minimum frequency for a light photon to produce photoelectric effect is called the threshold frequency. So they are related. E equals to HF, right? So if this is the work function, then this is my threshold frequency. They are proportional. So if the threshold frequency is high, then the work function is high. The energy needed to release them is also high. Different metal has different threshold frequency and thus different work function. So some things to take note. Okay, one more thing is that here, W, and then I supply it with energy. If there is photoelectron being released, okay, for electron to acquire kinetic energy, what is the condition? If you want the electron to get kinetic energy, your energy of the light must be bigger, right? Bigger than the work function for the electron to acquire kinetic energy. So E bigger than work function. So we have HF bigger than HF naught. Okay, cancel, cancel. So F bigger than F naught. Frequency of the wave must bigger than the threshold frequency. So we can say light frequency must exceed threshold frequency, okay, for electrons to have kinetic energy. This is seen from the threshold frequency perspective. Okay, just now we talked about the energy should be larger than work function, right? Because some question they will ask you the frequency instead of the work function. So the light frequency must exceed the threshold frequency for electron to have kinetic energy. Okay, we will go to the next one. Okay, next slide. Can we calculate the kinetic energy, and what is the method that we can use to calculate this kinetic energy of the electron So there's actually one experiment, okay, we can use to calculate the kinetic energy, which is using a photocell, okay? Now, basically, we form a circuit like this. We put a variable voltage, okay? We make a circuit like this. We put a photocell. Basically, it's like a tube, with no, it's vacuum inside, evacuated tube. And then I put two plates. One is cathode, one is anode. And this one, I shine the light on one plate. Okay, it must be a known frequency. You must know the frequency of this one. Okay, I shine the light on one plate, the cathode, and then it will emit electron, right? So electron will be emitted and move towards the other plate. Now you see, here, I purposely reverse the terminal. This is negative, this is positive. Here, okay, this is variable voltage, meaning that I can adjust the voltage. Okay, I can adjust the potential of this. Now, I connect in reverse. That means this is negative. Here would be negative. And here would be positive. Okay, normally we connect here is positive, right? So that it can attract the electron and the electron can go around the circuit. That is in your photocell, okay? Normally normal connection. But this one I purposely connect opposite terminal. Why? Because I want to find out what is the voltage to stop the electron from flowing to this plate. Okay, you see, I start from very small voltage. So when I shine the light and then I see, okay, I want to attach ammeter, okay, micro ammeter here. Then I will observe if there is a deflection in the ammeter, then that means that the electron can reach the plate. Okay, electron, they reach the plate and then they complete the circuit and then it shows the current here. Right, now I slowly increase the voltage. Then I'll find that this current started to drop. It started to decrease. Okay, why it started to decrease? Because as this voltage increases, this negative terminal, it will start to repel the electron. Because electron also negative charge, right? Negative charge, and as they try to move to the plate, this negative gets stronger and higher potential, then it will, at some point, it can stop the electron from reaching the plate. Understand? Okay, so that means if you shine the light here, electron is emitted, yes, but they are repelled by the negative terminal up here, so they cannot reach the plate. So at some point, when you increase it large enough, you'll see that here the emitter will reach 0 ampere. Okay, 0 ampere. That means no more current flowing. And when that happens, you know that the electron cannot cross already. Okay, so whatever the voltage used to stop the electron from reaching the plate, we give it a name for this voltage. We call it the stopping voltage. Okay, the stopping voltage. The voltage used to stop the electron from flowing to the plate. Now, why do we want to find the stopping voltage? The whole point of this, experiment is to find the stopping voltage. But what is it for? Now, you know that the voltage formula, V voltage equals to energy per coulomb of charge, right? E over Q. Okay, from here, the energy is given by the energy of the electron, half mv squared, and then the charge, I can just put E. This is charge of electron. Okay, so that means the voltage over here across this tube, the voltage across this tube is the same as this voltage, right? Same as this voltage. So if this is the stopping voltage, then this is the stopping voltage. So the stopping voltage is equal to the kinetic energy of the electron divided by the charge of electron over here. This is, we derive this one from the general equation of the voltage. Okay, because we know that for the electron to cross, it must have certain kinetic energy, right? And if the voltage is stopping it, that means the voltage having energy equal to the kinetic energy. That's why we put like this: Vs equals to half mv squared over v. Oh, sorry, over E. Yeah? Okay, now we do a little bit of arrangement. Then we have half mv squared equals to E Vs. Vs is stopping voltage, right? So from here, then I can say this is kinetic energy is equals to E Vs. Okay, EVS. So the kinetic energy of electron can be calculated using the formula of this one. If I take the charge, which is already a constant, right? 1.6 times 10 minus 19 coulomb. If I times into the stopping voltage, then I know what is the kinetic energy of the electron here. Where do I get this Vs? I get it experimentally from this. Okay, so if I know my stopping voltage, then I can calculate what is the kinetic energy of the photoelectrons. Okay, huh? Now take note of this. Okay, now once I know the kinetic energy, I can plot a graph to find the work function and the Planck constant. Okay, using this formula up here, Ke equals to E minus W. Okay, you see, Ke, let's just assume that we assume at the surface of the metal. Okay, at the surface of the metal is where the kinetic energy is the maximum, equals to E minus the work function. Okay, so given the work function is at the surface. From here, I can already get the Ke values, correct? I do this experiment for all frequencies of light. Then I get the kinetic energy of each frequency. I can plot a graph. Here I have a graph of Ke max, and then against frequency F. Okay, so I tabulate my result here for all values of frequency and their kinetic energy. And then I find that the graph looks like this. You can also predict this shape of the graph already, because Ke max equals to what? E minus W, right? So E is HF minus W, Ke max. And then you use your Y equals to mx plus C. Your Y is Ke max, your x-axis is frequency, and then you can see the gradient is H. The gradient is Planck constant. That means the gradient is a constant lah. So gradient is a constant. Your graph is positive, is a straight line. It's a straight line, right? It's a straight line graph, and also your y-intercept C is this minus W here. That means somewhere here, that is the work function. And then I draw my graph like this. When you plot it experimentally, you also will get this shape of the graph, similar to this one. When you can also predict it using the straight line equations. So a graph of Ke maximum against the frequency is a straight line like this. Now, few important points to take note for this one. Here is the work function, is a negative value, right? So let's say it's like -2 electron volt. Okay, so if the work function is -2, that means this over here, which is 2 electron volt, is the energy required to emit the electrons, correct? This one, energy required to emit electron from the x-axis down to the W. Okay, that is how much energy you need to emit the electrons. And if you see the point where it crosses the x-axis, where is it? Over here. Here it crossed the x-axis. What is the value of the Ke? 0, right? So this one is F, and then Ke is 0. What does it mean here? At this point, what does it mean? What is the condition? What happens when your Ke is 0? If your Ke is 0, that means the E is equals to the work function, correct? Because the energy of the wave, if it's equal to the work function, then the electron has 0 kinetic energy. Okay, only if it's bigger than the work function, it will have extra energy, right? So that means at this point, this F, the frequency where there's no kinetic energy, we call it the threshold frequency. Threshold frequency. I'll write this F note. So at the threshold frequency, the Ke max is 0. I repeat, when the frequency of the wave is the threshold frequency, the kinetic energy is 0. Okay, so this point here, the x-intercept, it tells you what is the threshold frequency of the metal, and this region here, down from the x-axis down to the W, it tells you the work function of the metal. Okay, so what about this graph here? Increasing, right? Increasing. So when you increase the frequency of the wave, when you increase the frequency of the light shining on it, you have more energy, right? You have more energy, so you minus the work function, you get more and more kinetic energy. That's why here the slope increases like this. Okay, so let's say you have this F1 correspond to this value. Okay, if the light is having a frequency of F1, then you have this much kinetic energy given to the photoelectrons. If your light is having a frequency that is same as the threshold frequency over here, then what is the kinetic energy? 0. Photoelectron does not have any kinetic energy. Okay, so it must be more than it to emit the electron. The frequency must exceed the threshold frequency. Okay, bullet point number 1 down there. Work function and Planck constant can be found using the photoelectric cell experiment. Okay, so this is the photoelectric cell experiment, what we discussed here. Okay, you can find it using the experiment. You calculate Ke, you plot all the values, you get the graph, and then you can calculate, okay, what is the work function? This one, the y-intercept, What is the Planck constant? Then we can measure the gradient of the graph. Yx over x, that is equals to the Planck constant. Point number one. Point number two, the stopping voltage gives us the maximum kinetic energy of the photoelectrons. Okay, the stopping voltage. When you achieve the stopping voltage, you know because the ammeter will turn 0 ampere. Okay, take notes and we will go to the next slide. Okay, finished. Here it is, huh? Okay, so here you can see a few examples of the work function of certain materials. We have cadmium, calcium, iron, nickel, and zinc. So here is our graph of kinetic energy maximum against frequency. Okay, again, you can see this one is the work function. This is the work function. So here the x-intercept is threshold frequency and the gradient is the Planck constant. This one graph represents one metal, one type of metal. If you plot other metal, then you have two curves on it. Okay, now oftentimes they'll kind of compare like this. We know that work function is proportional to threshold frequency, correct? W equals to HF. So W is proportional to threshold frequency. The higher the threshold frequency, the higher the work function. So if we have this metal here, different work functions. So which one is the highest? 4.5 iron. So sorry, nickel, 5.01. Right? So nickel has the highest work function. That means also it has the highest threshold frequency. So when you plot nickel in the graph, okay, somewhere here, 5.01, like this. Oops. Let me do like this. Okay. What is this? This is the threshold frequency of nickel. Can you calculate it? Yes, you can calculate, right? So you use this equation. Once you know the work function, you can calculate the threshold frequency. So this is nickel. Now let's say you want to plot iron, right? So iron having a work function of 4.5. 4.5, so somewhere here, 4.50. Okay, It's actually negative values, right? All these are negative values because you have the graph E minus W. Huh? So 4.5 means that the threshold frequency is also smaller than nickel, huh? Smaller than nickel. So the graph should go like this. Parallel, huh? They must be parallel. Why they must be parallel? This is the F naught for iron. Okay, this is iron and this is nickel. Why must be parallel? Because the gradient is the Planck constant. The Planck constant is the same for regardless of the material. So your graph should have the same two parallel lines. Okay, all the lines should be parallel. If you have 4 lines here, you should all of them should be parallel. Okay, and maybe you put calcium work function is only 2.10. Okay, somewhere down here minus 2.10, and then you have the line like this. This is the threshold frequency of calcium. Okay, so yeah, just for you to relate with the graph with the values of the work function and also the threshold frequency. And sometimes they don't show this region of the graph. Okay, they just draw like the first above the x-axis. So you have 3 lines like this. Okay, they show you 3 different metal. 3 different metal. Okay, this is the F node 1, F node 2, F node 3. Okay, nickel, iron, and calcium. A graph of Ke maximum against F. So that means choosing the right material also very important in your construction of the photocell. Okay, let's say you want to do a photocell and you want use light to create electricity. Okay, you want to use light to create electricity. So which material to choose? Do you choose the one with the high work function, or do you choose the one with the low work function? So understand the reason behind it. If you choose high work function, that means your light must exceed the threshold frequency. Your threshold frequency will be higher, of course. Okay, if you choose the one with the higher work function. For example, nickel. Okay, nickel here, it has the highest work function, so you need the most energy to create these photoelectrons compared to calcium, for example. Okay, so calcium, you don't need as much energy to emit the electrons. Here, right? A brief comparison between, okay, here we have calcium, lithium. Now, again, the connection shows a photocell. We use light to create emission of electrons, and there is a current produced in the circuit. Okay, so this terminal, this connection is the normal connection. So this is minus, it's positive, right? That means here is positive, here is negative. So once the electron emits, it will be attracted, okay, towards the positive terminal here. It will be attracted here. Same here, negative, positive. So once the electron emit, they will attract it. because they want the electron to flow in the circuit. So whenever there's light, electricity is produced. Okay, so it's like a photocell. What is a photocell? Your solar panel, okay, your solar panel, solar cell, it's the same concept. They work based on the same principle, the photoelectric effect. Your solar panel, you put it on top of the roof. When there's sunlight, then it create photoelectric effect, okay, and generate electricity to heat up, okay, heat up whatever, the water, anything, okay. Yes, or it can be, first is solar cell, right? Solar cell. Second is the, what you call that? The LDR, the light dependent resistor. That is also a photocell, okay, light dependent resistor. We use LDR in what? In automatic switch, right? We use it to do to construct automatic switches. So when there's light, what happened? When there's light, the resistance become very low. How come? So here you have your LDR. Okay, let's say you have the circuit. This is your LDR. This. When there's light coming, sorry, that is a resistor. Should be like this. Okay, like this, right? It's a symbol. So when there's light coming, when the intensity is high, what happened to the resistance? Resistance become very low. Why? Because when there's light, then it will create more electrons. It will create more electrons. Huh? So this is actually a semiconductor. In your semiconductor lesson, still remember or not? Your energy level. We got two, right? We got the valence band and we got the conduction band. When you have light shining on it, then it will give energy to the electrons. Those electrons will absorb this photon. Okay, it will absorb the photon and will jump to the conduction band, and you get more and more free electrons. Okay, so when the light shine on the LDR, more electrons gain energy. They jump to the conduction band, become free electrons, and then you get more free electrons. So less resistance. Okay, more free electrons and less resistance. So it becomes more and more conductive. That is why we say when the intensity is high, then your resistance becomes low. Okay, this is the LDR. It works based on almost the same principle as this one, right? Also caused by light. Energy given by light, by photon. The only difference is that for this one, the electron does not come out from the metal. It is only increase in energy level. They got excited. Okay, it excites the electron rather than pop out the electrons. Okay, electron is still inside. Right, and also when the intensity is low, when there's no light, then resistance become very, very high. Okay, that is LDR. So the application of it is solar cell, solar panel, okay, solar panel, and even the International Space Station, the satellites, right? They use solar panel to create electricity. You cannot send a generator up there, right? So you need solar panel as the electrical source. So solar cell and also LDR. Okay, quick comparison. You see, caesium. The work function of caesium is 2.14 electron volt. So using this one, you can calculate the threshold frequency. You'd have W equals to H threshold frequency. Then you get the threshold frequency 5.16 times 10 power of 14 hertz. Okay, and then you see maximum wavelength to produce photoelectric current. What does that mean? V equals to F lambda, and V over lambda equals to F. If your F is a threshold frequency, that means if there is a minimum frequency to produce photoelectric current, because wavelength is inversely proportional with frequency, that means there is a maximum wavelength to create photoelectric current. Again, okay, lambda is inversely to the frequency, right? So if we have a threshold frequency, which means if we have a minimum frequency to emit the electron, that means we also have maximum wavelength to emit the electrons. So that's why it says here the maximum wavelength to produce photoelectric current. If you have wavelength higher than this one, then electron will not be emitted. Okay, so it could be highest is this one, 579, and it can be lower, but not higher than this one. Same as the frequency. You can be this one or higher, but you cannot go lower than this threshold frequency. This is for calcium metal. For lithium, different, right? Work function is 2.5 higher. The threshold frequency is also higher, but the wavelength is lower than the calcium because inverse relationship, right? So we can say that in general, the higher the work function, the shorter the maximum wavelength required to produce photoelectric current. What about the light intensity? The light intensity, if I increase the brightness, okay, intensity is brightness. If I increase the brightness, what does it mean? Do I increase the energy? No, okay, no, because the particle theory does not say that brightness is energy. No, that is from the wave theory. So if you increase the brightness, you're actually increasing the number of photons arriving per second. Okay, so please take note of this. Intensity or brightness, it means number of photon arriving per second. So if you increase brightness, it means more photon coming in 1 second. How does it change my circuit here if you have more photon coming? Let's say you got 10 electron. Okay, the first one is low brightness. Low brightness means, let's say you got only 2 photons per second arriving. So this 2 photon is going to absorb by the two electrons. Okay, so 1 photon absorbed by 1 electron. So 2 photon coming, 1 second you can emit 2 electron only. Okay, 2 electron emitted in 1 second. Every second 2 electron emit. But if you increase the brightness, let's say you have 10 photon coming per second. All of this will be absorbed by, okay, each of the photon will be absorbed by the electron. So in 1 second, how many electrons you are emitting? You are emitting 10 electrons emitted. Okay, in 1 second, you got 10 electron emitted. So you got more electron emitted in 1 second. So how does it change the circuit? It changes the current of the circuit, right? Because current is the flow of charges. So if you have more electron flowing, more electron emitted, then your current will increase. So as light intensity increases, the photoelectric current also increases. That is the last point. Okay, so take a rest, 3 minutes, and I will show you just a few examples. Okay, then I'll give you exercises. Okay, let's look at a few examples. Come back here. What is the work function of potassium if green light with a wavelength of 510 nanometers shining on it produces photoelectrons that have maximum kinetic energy of 0.14? Okay, find the speed of the photoelectron. All right, so we have, what do we want to find here? What is the work function? We want to find the work function, correct? So what do we know about the formula of work function? We have Ke equals to E minus the work function, right? And we know that this one is E equals to HF. But given in the question is the wavelength. So we can first calculate the energy of the green light, the energy of the green light. So using E equals to Hc over lambda. Okay, how much is this? Let's do the calculation. So we have Planck constant, 6.63 times 10 minus 34 times into speed of light divided by nanometer. Yes, okay. Okay, I get 3.19 times 10 minus 19. Energy in joule. Okay, and then it says that it produces photoelectron that have a maximum kinetic energy of 0.14. So meaning that this kinetic energy are the maximum 0.14 electron volt. This one we want to change it to joule. So we multiply, you want to change it to joule, then you multiply 1.6 times 10 minus 19. Okay, because one electron volt, if you want to change to joule, you times the charge of the electron. So 1.6 times 10, 19. Okay, what do we get? We get 2.24 times 10 minus 20 joule. Okay, then work function, work function equals to E minus KE. Okay, we'll calculate this. $2.9. Where's my mouse cursor? Something's wrong with my mouse cursor. Wait. Suddenly I cannot see my mouse cursor. Wait. Okay. So this one is 2.9 times 10 minus 19. Okay, something's wrong here. This one should be This one should be 3.9. Okay, let me erase this. This is 3.9 times 10 to the power of negative 19. Yes. So this is 3.9 times 10 to the power of negative 19. Okay, so you get 3.68 times 10 minus 19. Okay, so that is the work function. Now from here, you can get the speed of the photoelectron, right? Because you already know the kinetic energy. So kinetic energy maximum, that's half mv squared equals to 2.24 times 10 minus 20. Okay, we can find the V. So V squared equals to 2.24 times 2, and then you divide by the mass of electron given here, 9.11 times 10 minus 31. Okay, you can take a square root of this. 221758. Okay, approximate 2.22 times 10 to the power of 5 meter per second. That is my answer. Okay. Okay, next question. Figure shows the change in kinetic energy of photoelectron released from lithium for different light frequencies. Determine the threshold frequency from the graph and calculate the work function of lithium. Okay, so we get the threshold frequency, the x-intercept. So we have the kinetic energy against the frequency graph, right? So the x-intercept is the threshold frequency. Now this one is about, okay, we just approximate about 5.6. Don't forget this one, 10 power of times 10 power of 14 hertz. So our F note is 5.6, 10 to the power 14 hertz. And the question wants you to find the work function, W, H, F note, 6.63 minus 34 times into 5.6 times 10, 14. Okay. Answer is 3.71 times 10 minus 19 joule. The last example. Okay, when a photocell is shown on with a red light and then with a blue light, the maximum kinetic energy of the photoelectron emitted by the blue light is 2 times of the red light. So that means the kinetic energy of the blue light, KEB, equals to 2 times the kinetic energy of red light. What do we want to find here? What is the work function of the photoelectric material in the photocell? We want to find W. Again, our equation from A, KE equals to E minus W. So we can write, okay, KE red equals to the energy from red light minus work function. And another one is the blue one, right? So we know that the blue is 2 times of KE red. So I'll just write 2 KE red equals to the energy from the blue light minus W. The W is the same, right? So I'll just leave it the same like this. okay, because they are shine on the same material. So that is my equation 1, equation 2. Okay, continue. Now, from here, maybe I can move the ER as the subject. Here, ER equals to KER plus W. Here I have my equation 1. And the other one here, I move EB equals to 2 KER plus W. Now, I want to calculate the W, right? So I want to solve this simultaneously. Okay, I'll just use the elimination method. So I can just cancel out the KE. This one, the KER is the same. I can just cross off. But I have to take equation 1 times 2 minus equation 2. Okay, equation 1 times 2. So we have this one times 2, we get, let me use a different color here. 2 ER equals to 2 KER plus 2W. And then we have our EB okay, then we minus lah. Minus ER minus EB equals to this one cancel. So with 2W minus W equals to W. Okay, so like this, then I can put in the values, So I know that energy is, this is energy from the wave, right? So it's hf. Or if it's given in wavelength, then you can use hc over lambda. So 2 bracket, the red light hc lambda red minus hc lambda blue equal W. Okay, then the rest is just calculation. Red light 75. Remember to change it to meter. All must be in SI unit. Okay, equals W. Then calculate this. And what is the final answer? Give me a second. This one is 5.304 times 10, 19 minus okay, this one is 4.324 times 10 minus 90 equals to what? I'll just bring it in front. So 9.8 times 10 minus 20 joule. So that's our answer. For A. B, what is the threshold wavelength of the photoelectric material? So we have work function equals to H threshold frequency, V equals to F lambda V over lambda. If this is threshold frequency, then this is threshold wavelength. So W equals to H V over like this. Okay, so you already have the values. 9.8 times 10 equals to 6.63. 3 times 10 to the power 8 over lambda threshold. Okay, so answer is 2.03 times 10 minus 6.